In math, we usually think of numbers as exact, so that 3, 3.0, and 3.00000 all represent the same number. But in science, we deal with measurements, and measurements can never be perfectly exact. When we hear a measurement, we assume that the way it is stated tells us something about what was measured. More specifically, if these numbers represent measurements, then we say that they differ in their precision. 3 is the least precise, and 3.00000 is the most precise. An example should clarify the idea. Suppose you weigh yourself on a scale that can be read reliably only to the nearest kilogram, and it shows that you weigh 61 kilograms. It's fine to write your weight as 61 kilograms, of course. But if you write it as 61.0 kilograms, you're implying that you know your weight to the nearest tenth of a kilogram, but you don't. More formally, we say that the first number is precise to the nearest kilogram, while the second is precise to the nearest tenth of a kilogram. The first number is fine in this case because you really did measure your weight to the nearest kilogram, but the second stretches the truth because it implies you measured to greater precision than you actually did. This leads to an important general rule. You should never state a number with more precision than is justified, because doing so implies you know more than you really do. The basic idea is simple, but in some cases the precision of a number may not be obvious. For example, suppose you read that some ancient ruins are 1400 years old. Without further information, you would have no way to know if this number is precise to the nearest year, meaning exactly 1400 years, to the nearest 10 years, or to the nearest 100 years. We therefore need simple rules to decide which digits in a number are significant, meaning digits that represent actual measurements. Here are the rules. Most are probably obvious. Non-zero digits are always significant, since you wouldn't write them if you didn't measure them. For example, both digits in the weight of 61 kilograms are significant. In between zeros are significant. For example, a measurement of 505 meters has 3 significant digits because you must have measured 0 tens in order to measure the 5 ones. Zeros after a decimal point are significant because there's no reason to write them otherwise. For example, 46.00 kilograms has 4 significant digits because the zeros after the decimal point should not be there unless they were measured. The only time digits are not significant is when you have zeros that serve only as placeholders. Sometimes zeros hold places to the right. For example, this 1400 years could also be called 14 centuries, suggesting that the 2 zeros that follow the 14 are only placeholders. In other cases, zeros hold places to the left. A measurement of 0.005 seconds can also be called 5 milliseconds, telling us that the 2 zeros to the left of the 5 are just placeholders. One problem that can arise is when you have zeros that you've measured but that are not significant by these rules. For example, suppose you really do mean 1400 years to the nearest year. You can't tell from writing it as 1400 because the rules imply that the 2 zeros are not significant. However, if you write it in scientific notation with the zeros included, then we know that the zeros are significant because the rules tell us that they would not be there unless they were actually measured. Before we conclude, it's worth noting that although they are sometimes used interchangeably in ordinary English, precision and accuracy are not the same thing. To see the difference, suppose you actually weigh 61.2 kilograms, and you then measure your weight on 2 different scales. First, you try an old-fashioned scale that you can read reliably only to the nearest kilogram. It says you weigh 61 kilograms. Next, you try a digital scale, and it gives a clear, repeatable readout of 63.74 kilograms. The digital scale is more precise because it is giving you your weight to the nearest hundredth of a kilogram rather than the nearest kilogram. However, the old-fashioned scale is more accurate because its reading is closer to your true weight of 61.2 kilograms. To summarize, accuracy describes how closely a measurement approximates the true value, while precision describes the amount of detail in the measurement.